have Professor Rukmani Mohanta, and so she's an expert on flavor physics, heavy flavor physics, and neutrino physics, and she got her PhD from Utkal University in India, then moved on to Punjab University, and since 2000, she's a faculty member at the University of Hyderabad, and since 2015, a full professor. So she is, as I already said, an expert on heavy flavor physics and neutrino physics, looking there at model building and to try to explain anomalies and to basically understand that sector better. And since 2013, she is also a member of the NOVA collaboration, and since 2016 of the DUNE collaboration. But today it will be a talk about theory, and she will be telling us about recent flavor anomalies and their implications on invisible sectors. So please.
Yeah. So hello everyone, and thank you very much for the kind introduction. It's a great pleasure and honor for me to visit UNSW as a Gordon Godfrey visitor, and thanks to Michael for hosting me. So today I'm going to talk about recent flavor anomalies and their implications on invisible sector. So as we know, the standard model is a very beautiful and elegant theory. It explains almost everything that we have seen in the collider so far. However, despite its tremendous success, it can be regarded as a low energy theory of a more fundamental theory. And we need to find out what is the fundamental theory. So far, we have not seen any clear signature of new physics either at the intensity frontier or energy frontier. But there are many issues which standard model doesn't provide any successful answer. For example, from many observational evidences, we know that the dark matter exists, and the energy budget of the universe, it gives us the idea of the dark matter, which is around 27%. So to explain the existence of dark matter, one requires new weakly interacting massive particle as one example. Similarly, from various neutrino oscillation experiments, we know that neutrinos, they do possess small but non-zero mass. And in the standard model, neutrinos are exactly massless. So to explain this non-zero neutrino mass, one requires right-handed heavy neutrinos, which are known as sterile neutrinos. Similarly, standard model, it cannot explain the observed baryon asymmetry of the universe. So we require additional CP violating interactions. So the obvious question is that standard model, it has to be extended, and how to go beyond the standard model and to find out the underlying fundamental theory. So hopefully flavor physics will provide some interesting light in this direction. So searches for new physics, it can be done in two ways. The first one is through direct production at colliders, which will produce new heavy particles, and we can directly observe the properties of such heavy particles. But so far, we have not seen any kind of new particles. And the second method, which exploits the presence of virtual states, and due to this quantum mechanical effect, the intermediate states, they can be much heavier than the initial and final states, and we can get indirect evidence from such virtual particles. The most familiar example is the beta decay process, and we know that in beta decay process, the energy released is of the order of MeV. However, it gives us the physics of at W scale or W mass scale, which is around 80 GeV. So analogously, the flavor observables, which are quite sensitive to high energy scales, they can be observed, and we can get the signature through virtual effects. So there are many heat factories or heavy flavor factories at which we can have huge number of heavy particles are produced, and those particles, they can decay to light particles. By studying their properties, if we find some mismatch between the experimental results and their corresponding standard model predictions, it would hint towards the existence of new physics. And another interesting feature of flavor physics is that flavor physics, it can probe new physics at much higher scale than the direct searches at Collider. For example, at LHC, with energy of 14 TeV, we can directly produce the new particles up to energy up to mass of 7 TeV. However, if we go to flavor sector, for example, the anomalies at B to S mu, they can probe the new physics scale up to 30 TeV. Similarly, for lepton flavor violating mu to E 3 decays, they can probe the new physics scale up to 10 to the power 2 TeV and so on. So what are the importance of flavor physics? Flavor physics encompasses many open questions of the standard model. For example, why there are 3 generations of quarks and why the quark masses are so hierarchical in nature, why the quark and mixing matrices are quite different. Most importantly, the flavor physics, it serves a tool to discover new physics beyond the standard model. So coming over to heavy flavor physics, there are 3 main pillars. The first one is the CKM mixing of the quark sector and the corresponding unitarity triangle. Then the neutral meson mixing. And the third point or the third pillar is the rare decays, which is associated with flavor changing neutral current transition, for example, B to S or D. Now the CKM matrix, which relates the weak eigenstate D prime, S prime and B prime to the corresponding mass eigenstates D and S and B. And this matrix is unitary. This 3x3 matrix unitary, to parameterize this 3x3 unitary matrix, we need 3 mixing angles. These are the 3 mixing angles and 1 CP violating phase. This phase is the origin of CP violation within the standard model, and the amount of CP violation can be characterized by this Charles-Cox invariant, and the value of the Charles-Cox invariant or the CP violation is of the order of 10 to the power minus 5 in the standard model. However, this amount of CP violation is not sufficient to explain the observed baryon asymmetry of the universe. So we need to go beyond the standard model, or we need to have new sources of CP violation. So the CK paradigm, that is the mixing matrix, which contains 3 mixing angles and 1 phase, it explains CP violation within the standard model, but this one is really not sufficient to explain the observed baryon asymmetry of the universe, for which we require of the order of 10 to the power large CP violation effect. Now this unitarity condition of CK mixing matrix can be parameterized by this relation, or this is one of the relation, that is the unitarity conditions. It gives the multiplication of one row and the complex conjugate of another row. So this can be one such equation, and this equation, it can be represented as a triangle in the complex plane, and this particular triangle is important because the 3 sides of this triangle are of equal size. So the 3 angles of this triangle are known as alpha, beta and gamma, and the prime objective of the B factory experiments is to very precisely determine this unitarity triangle. So if we look into the various measurements, we can see that the triangle is very severely constant, but still there is room for new physics at the level of 10%. Now coming over to the results that we have known from B sector. So these are the things that we have already known. That is, CP violation in B system is established. CKM mechanism is the source of CP violation. So for which Kobayashi and Moskova, they got the Nobel Prize in 2008. Most of the data from B factories, they are they are in very good agreement with the standard model prediction. However, there are some results which are associated with flavor change neutral current transitions. There we can have new physics contribution at the level of 20%. Though we have not seen any clear evidence of new physics from the B sector, there are several anomalies for which the deviation from the standard model expectation is at the level of 3 to 4 sigma. So the next generation flavor experiments will improve the sensitivity by almost 1 order. So the overall new physics sensitivity is of the order of dB region if we have the standard model like flavor violation, and if we consider less constant theories, then the scale of new physics, it could be from 10 to 100 dB. Now coming over to one of the important issues, which is known as lepton flavor universality. This is one of the key ingredient of the standard model. In the standard model, the coupling of the case bosons W and Z to various leptons are universal. That is equal coupling for W and Z bosons to electron muons and tauons. However, the Yukawa sector, it violates the lepton flavor universality. That is, this is the Yukawa term, and as we know, this Yukawa term, it gives the masses of the particles. So from this term, we can see that the masses of the 3 charged leptons, they are quite different. They are not same. So, however, the Yukawa sector, it doesn't play a major role in the flavor physics sector. Therefore, we can usually expect that the lepton flavor universality, it remains valid in the flavor sector. So we can say that the lepton flavor universality is enforced in the standard model by construction, and any violation of it would be a clear signature of new physics beyond the standard model. Over the years, the lepton flavor universality violation has been searched in various systems, for example, Z to LL, W to L nu, Jepsi to LL, and so on. And it is found that this lepton flavor universality, it holds good in all these decay channels. So they provide very strong limit on lepton non-universality in the electroweak sector. However, in recent times, we have seen several anomalies which violate this lepton flavor universality. So these deviations, they are not statistically significant enough to claim the absolute discovery of new physics. However, at the same time, they are also not weak enough to be completely ignored. So we can categorize these anomalies into 3 different channels. The first one is lepton flavor universality in the charge current transitions B to C L nu, and these are known as RT and RT star. Similarly, if we consider the flavor changing neutral current transitions B to S mu mu, there we have seen several deviations which are known as P5 prime, branching ratio of B to K star mu mu, BS to phi mu mu, and so on. And these decay processes, they are mediated by B to S mu mu transitions. Similarly, another anomaly which is similar to this RD star but associated with B to SLL transition, and with the recent data, this anomaly has been resolved. However, it plays an important role for the last nearly 1 decade or so. It is the central stage of flavor physics. Now let us define what are these anomalies. So RD star or RT or RD star, this observable is related to the ratio of branching fractions of branching ratio B to D star tau nu to corresponding B to D star L nu. So if lepton flavor universality holds good, then we expect that there should be whatever be the standard model prediction, it should be same as the experimental value. However, these are the corresponding standard model predictions. We can see that the experimental values by 3 different experiments, Bell, Babar, and LHCb, there is significant deviation from the corresponding standard model predictions. Though individually, the deviation is at the level of 1.4 sigma in RT and 2.8 sigma in RD star. If we take the correlation between RT and RD star, the overall discrepancy between the theoretical prediction and experimental observation is 3.2 sigma. Similarly, about 3 sigma deviation from the standard model prediction is seen in these observables, which are from 3 different experiments, and they use different tagging methods. However, if we take the corresponding observable with E and mu in the numerator and denominator, the corresponding observables, they are quite consistent with the standard model. In the standard model, this ratio is expected to be 1. However, experimentally, it is found to be this value. In addition, Bell has also measured several other observables which are associated with B2C tau nu transitions, but these are more or less consistent with the standard model. Another observable which is similar to RT and RD star, but it is associated with BC transition. This one is known as R psi, BC going to psi tau nu, and BC going to psi mu nu. This value is this one, this much, and it deviates from the standard model prediction at the level of 2 sigma. So if we consider the new physics to affect only to B2C tau nu transition, and there will be 10% enhancement in B2C tau nu transition, because here the theoretical ratio is greater than the standard model prediction, which implies that the new physics, it will contribute only to this one. So if we consider 10% enhancement to B2C tau nu transition, then we can get the new physics scale of the order of 3 TeV by confronting these two relations. Similarly, one can define the lepton flavor universality violation in flavor changing neutral current transition B2SLL in the analogous way. Here, RK and RK star, they are the ratio of branching fractions of B2K to mu mu and B2KEE. Within the standard model, the expectation of this lepton non-universality observable is of the order 1, with uncertainty at the level of 10 to the power minus 3. However, in 2014, LSCB, it measured the value of this lepton flavor non-universality observable in the low Q square bits, and it gave the deviation of around 3 sigma, 2.6 sigma. So before then, it was measured again by LSCB and with improved statistics. And before December 2022, this was the situation. LSCB measurement with 3 inverse is this one, 5 inverse is this one, and this one is in December 2021, which gave the deviation around 3 sigma. However, in December 2022, LSCB again released the updated data on RK star measurement, and here they used improved statistics and a tighter selection rules for the electrons, and they found that these ratios, they are consistent with the corresponding standard model predictions. In addition to RK and RK star, they also measured the value of RK plus, and these are the corresponding measurements. So we can see that these experimental measures, they are in agreement, or they are in agreement with the corresponding standard model prediction. Next, we come to another decay mode, which is B2K star mu mu. Since in this case, K star, it decays to K pi, so the angular distributions, from the angular distribution, we can extract the different observables, and from these observables, we can construct the form factor independent observables, which are more or less clean observables, and they will be independent of the form factor uncertainties. So these optimized observables, they are measured by LSCP at LAS and CMS, and for P4 and P5 prime, in these two bins, LSCB observed some deviation which are at the level of 3 sigma. Atlas also observed 3 sigma deviation in 4 to 6 bin, and these are the Atlas results from for P4 prime and P5 prime. So roughly, although the lepton flavor universally violation or lepton flavor universally violating observable is inconsistent with the standard model, the optimized observables, they still show some anomaly at the level of 2 to 3 sigma. Similarly, for the charge current B transition, there are again anomalies in P2 and P5 prime. So if we consider 24% deficit in the standard model muon channel, then we can get the scale of new physics, which has to be 30 TeV. If we consider new physics to contribute at the T level, and if we consider new physics to contribute at the loop level, then the corresponding scale will reduce to 3 TeV. Similarly, there are several branching fractions which are mediated by B to S mu transition. They show systematically the experimental data are systematically lower than the standard model predictions in various decay modes which are mediated through this B to S mu transitions. Another interesting decay mode is BS to mu. This one is mediated in the standard model. This one is highly suppressed. It is mediated through the loop level processes, box and penguin diagrams. So theoretically, this one is very clean. However, it is loop suppressed in the standard model as well as CKM suppressed and helicity suppressed. Till 21, there is around 2.3. These are standard model predictions, and these are the corresponding world average values of LSCB, CMS, and Atlas. And we can see that there is 2.3 sigma discrepancy. Since this process is very clean, it was expected that this would provide the clear signature of new physics. However, recently LSCB as well as CMS, they released their new result, and it is found that the branching ratio of BS to mu is now consistent with the standard model prediction at the level of 1 sigma. So this is the list of anomalies which are associated with the flavor sector. So apart from the branching fractions and RD star as well as P5 prime, more or less all the data, they are consistent with the corresponding standard model prediction. So now the question is how to address these anomalies in the B sector. So as we have seen that the scale of new physics in the charge current transition B to CLU and B to SLL, they are quite different. So if we consider the new physics contribution which contribute with single mediator like W or W prime for B to C and Z prime for B to S, it will not work because the scales are quite different. However, if the new physics, it arises at T level to the charge current transition and at the loop level for the neutral current transition, then the scales are more or less similar. So we can explain all the anomalies in a single platform. So what we have to do is first we have to construct the effective Lagrangian, which might explain the experimental data. Then we have to find out the new particles which can mimic the effective Lagrangian, and then we can check all other low energy flavor constants. And then we have to construct the consistent model for new physics. So one of the familiar or one of the usual approach is the effective field theory approach. In this approach, we consider the additional new physics contributions which are often assumed to be real, and we add these new Wilson coefficient to the standard model Wilson coefficient so that we have the effective new Wilson coefficient. Then considering the set of observables, we can extract the values of these new Wilson coefficients and then constant the values of the corresponding new physics parameters. Now coming over to B to C tau nu tau transition. Here, the most general effective Lagrangian or effective Hamiltonian we can write in the complete set of these basis currents like VL, VR, scalar left-handed current, scalar right-handed current, and tensor current. And these are the corresponding structure of the four fermion interactions. This is the LL current, which is there in the Standard Model, and all other rest of the four fermion currents, they will arise at some new physics model. So, as I mentioned, by considering different set of observables, one can fit and get the values of the new Wilson coefficient. So, this fitting has been done by many authors, and from these fittings we can notice that the most preferable new physics structure, it comes or it has the flavor structure of LL type of current. So the bottom line coming from this B to C tau 9 mu transition is this OVL has the same structure as the Standard Model, hence it gives the same enhancement to both RD and RD star, and it will be proportional to 1 plus CPL mod square. So this is the most preferred scenario. However, if we consider the right-handed current, then it will give the new physics contribution to RT as 1 plus CPR square type and to RD star this much. However, in both these ratios, we have seen that the experimental data is greater than the Standard Model predictions. Therefore, simultaneously, we cannot explain both RD and RD star. So this one is not the preferred solution. Similarly, this scalar type or scalar structure, it predicts, they although preferred scenarios, they predict large branching ratios for BC to tau nu. Hence, they are constant by BC lifetime. Next, coming over to B to SLL transition. So here, these are they arise at one loop level in the Standard Model, and this is the corresponding effective Hamiltonian, which describes B to SLL transition. And these are the corresponding four fermion interactions. Here, the most important contributions to B to SLL transition are C9 and or O9 and O10, and the corresponding Wilson coefficients are C9 and C10. In addition, we can also have the scalar and pseudoscalar type of interaction. So again, various groups, they perform the fit, and the most preferred scenario for explaining the anomalies in B to S mu transition is C9 mu. The new physics, it will contribute to muon sector, and the preferred scenario is C9 NP muon. It should be same as minus of C10 NP mu. Now, after the recent observation of RK star, because it is consistent with the Standard Model, so people try to check whether the new physics, which will contribute to only to B to S mu transition, it still holds good or not. So this is if we consider no new physics contribution to B to SEE, then this is the this green region is coming from the PS to mu data. This one is coming from RK and RK star observable, and this orange region coming from all other B to S mu transitions, which are branching fraction P5 prime or optimized observables and so on. So there is some discrepancy between RK and RK star and all other B to S mu observables. So since there is some type of tension between the fitting with B to S mu observables and RK star observable, therefore another possibility is that there will be new physics contribution to both B to S mu and B to SEE. So that one is known as universal. And in addition, since we are observing also deviation in B to S mu, there will be some new physics contribution to B to S mu. So this gives C9BS mu mu as universal plus some additional contribution, whereas for B to S EE, this will be only universal contribution. Now, fitting to both B to S, BS to mu mu and all the optimized observables and RK star, the best fit values are found to be C9 universal is this much, and the additional new physics contribution to B to S mu mu is this much. So we tried to explain, this one is before the latest measurement of RK star. We tried to consider vector lepton quark, which one is 3, 1, 2 by 3, and try to explain both B2S mu mu as well as B2C tau nu anomalies on a single platform. So since this vector lepton quark, it mediates B2S tau nu as well as B2S mu mu at the tree level. So we can write the corresponding Lagrangian density, interaction Lagrangian in this form. There will be coupling between the quark doublet and lepton doublet, and down type quark and charged lepton right-handed, and the vector-like quark and scalar diquark. This scalar diquark is introduced because we have to also we need to also try to explain the neutrino mass on this framework. So once we expand the terms here in this interaction Lagrangian, this will give the new contribution to B2C tau new transition like CVL and CSR. There will be 2 additional new contribution, and it will give to B2SLA transition like C9 equal to minus C10, C9 prime equal to minus C10 prime, 10 prime, and so on. So by including all these new physics contributions, we consider all the observables that we have, RD star, RK star, and all the B2S mu mu observables, and we tried to fit and we got the values of the lepton-quark couplings. Here we have used the lepton-quark mass to be of the order of 1.2 TeV. So these are the best fit values and the corresponding 1 sigma and 2 sigma allowed regions. So these are the examples of the coupling of the lepton-quark to the corresponding quark and lepton only of the form of left-handed type. Once we get the lepton-quark coupling to quarks and leptons, we try to study various lepton flavor violating decays in B meson as well as tau lepton sectors, and it is found that they can give or they provide significant enhancement with respect to the corresponding standard model predictions, and they could be observed in the upcoming LSCB experiments, within the reach of the LSCB experiment and as well as Bell 2 experiments. So one can, since we have a vector lepton quark and scalar diquark, we can also generate the neutrino mass at 2 loop level through the radiative mechanism, and this is the expression for the neutrino mass. We can do this is the corresponding loop expression, and we can integrate out, and we can see that whatever be the lepton-quark couplings that we obtain from flavor sectors, and considering the lepton-quark mass to be 1.2 TeV, we get the allowed region in the this coupling as well as diquark mass. So we can successfully also explain the neutrino mass in this framework. Now, it is believed that the Z prime as well as the lepton-quark, they are the 2 possible scenarios which can explain the flavor anomalies. So we also try to explain the Z prime model, which is associated with this gauged L mu minus L tau model, along with one scalar lepton-quark S1 U1 13. So in this model, in addition to this L mu minus L tau model, we consider in additional lepton-quark. So we know that the standard model has some accidental symmetry, that is the period number and lepton number, they conserve. However, they become anomalous if we promote this global symmetry to a local one. So to cancel the gauge anomalies, we need to include some right-handed neutrino with appropriate B minus L charges. However, if we consider the symmetry as L mu minus L tau or L alpha minus L beta, such local gauge symmetries, they are automatically anomaly free. And another important point of this L mu minus L tau gauge symmetry is that the Z prime boson, gauge boson, doesn't couple to either electron or proton, which implies that the constants which are coming from LSC or LEF, they are not directly applicable to such gauge boson. So these are the particle content of our model. In addition to the standard model particles, we have 3 right-handed neutrinos. We have 3 additional or 2 scalars. This one, it breaks the U1 L mu minus L tau symmetry. This one is inert, or it doesn't get the wave, so that we can explain the neutrino mass matrix at the one loop level. And this S1 is a scalar leptoquark, so that we can couple to the quark sector. And this one is the corresponding gauge boson. Now we can explicitly write down the corresponding Lagrangian. This one is the gauge Lagrangian. This is the fermion Lagrangian. These are Majorana mass terms. This one is Yukawa mass term, and this one is the coupling of scalar leptoquark to the new right-handed fermion and the down-type quark. This is the gauge fermion interaction, and this is the scalar term. So since we have 2 U1 gauge symmetries, U1Y and U1 L mu minus L tau, these gauge bosons, they mix with each other, and for their mixing, we consider this GL2R transformation. And in the basis of W mu 3, B mu, V mu, this is the corresponding mass matrix. We need to diagonalize this mass matrix to get the masses of MZ, MZ prime, and W. Similarly, in the scalar sector, there will be mixing between the 2 scalars, this eta and phi, and after the diagonalization of the scalar sector mass matrices, the lightest mass, it corresponds to the standard model Higgs, and the other one is the heavier Higgs. Similarly, the 2 masses in the fermion sector, they mix with each other, and the lightest one, it acts as the dark matter. So these are the representative set of masses and the other mixing parameters that we consider in our analysis. So since this lightest fermion, it acts as a dark matter, it can decay to mu bar, tau tau bar, as well as the corresponding neutrinos through Z prime and eta portal, and to this down type quark sector through T channel scalar diquark portal. So we can calculate the corresponding relic density, and it is found that this Z prime portal S channel, it gives or it explains the corresponding observed relic density, which is given by the Planck data. So coming over to the direct detection prospect, we consider the spin dependent cross section from this expression, and for the set of the various parameter values that we have considered in our analysis, it is found that the direct detection cross section is well below the CDMS light. So it successfully explains both neutrino masses as well as dark matter observables. Now coming over to considering the various parameters from flavor sector. Here we this combination of the scalar leptoquark and the heavy fermion, they mediate B to SLL transition as well as B to S gamma transition at one loop level, and we can see that the dominant diagrams which give the new contribution to B to SL transition are given in this diagrams, and basically they give new physics contribution as C9 prime. So the new parameters which appear in this new Wilson coefficient are the Yuka coupling, the gauge coupling, and the mass of the Z prime mass. So we can get the constant on this Yuka coupling, gauge coupling, and Z prime mass from the B2S mu mu observables, or RK, RK star, and B2S gamma observables. So we have the allowed parameter space in this gauge boson coupling constant and gauge boson mass, as well as the Yuka coupling and the dark matter mass region. So this region is allowed by imposing all other constant from various other experiments. So we considered two different, or these are the allowed parameter space for the Yuka coupling, gauge coupling, mass of the dark matter, and Z prime boson. So since the Z prime boson is very light, and we are considering the dark matter mass to be less than 2.5 GeV, we can see the implication of our model in B2SE transition or B2S missing energy type of decay transitions. Now, in the standard model, this B2S plus missing energy, it can be described only through B2S nu bar transition. And in the standard model, this B2S nu bar transition is given by this expression, whereas this there will be no right-handed neutrino, so this term will be 0 in the standard model, and only this term will be non-zero. So these are the corresponding four fermion interactions, and the Wilson coefficients are given by this expression. So in the standard model, we can calculate the B2S nu bar transition for three different kind of processes: B2K nu bar, B2K star nu bar, as well as BS2 phi nu bar. However, for these processes, we do not have so far the measurements. We have only the upper limits, and the standard model predictions are well below the existing upper limits. So if we consider the process of B2S plus missing energy as a combination of B2S nu plus B2S n minus, this is the dark matter component, because this is also invisible. So now we need to calculate what will be the expression for B2S n bar in this model, and this is the dominant loop diagram which gives or which contributes to B2S n bar. So this gives the new Wilson coefficient like this, which depends on the Yuka coupling, gauge coupling, the mixing parameters, as well as the Z prime mass and the corresponding loop function. So we have considered some benchmark values like this, and for Z prime mass 4 GeV and 4.8 GeV. However, when we consider the mass of Z prime to be 4 GeV, then there will be some pole or singularity at q square equal to mz prime square. So we need to use some cut to remove that singularity. So these are the corresponding predictions for two sets of benchmark values, and if we combine the this branching ratio with the corresponding B2S nu bar transition, then we can still we see that there is slight improvement than the corresponding B2S nu transition, and they are still below the experimental upper limits. So this brings to the end of my talk. So we have seen that the current anomalies in the flavor sector, it provides an ideal platform to look for new physics. They have huge impact on model building and also in the searches for new particles like lepton quarks and Z prime. Though building a viable model which accommodates the observed B anomalies and consistent with all other measured flavor observables is difficult, but the models with lepton quarks seem to address all anomalies along with some additional assumptions. So thank you.
Thank you very much. So we have time for questions. Who would like to go first? I'm also checking at the screen. Maybe let me start, and while people have time to think about questions. So in the end, you basically looked at has that light set prime and
Yes.
everything light,
Yes.
and with that Q-squared distribution. So bar, they present the results binned in Q-squared.
Yeah.
So in principle, that resonance should show up in one bin.
Yeah.
Right?
Yeah. We
Did
have
you
not
check?
checked. No, we have not checked the binwise Q-square distribution.
Mhm. Yeah. Thanks. Did you see any other things? So because they have now Q-square dependence for those particles, how about other observables? Would it affect their the prediction, or how much would it affect the prediction? I mean, for B2SLL or for B2.
For B2SLL, we have used the experimental data to fit the different parameters of the model. So we are not using to see the distribution in B2SLL transition. We are just trying to see what will be the implication in B2S nu.
Okay.
So we are trying to use the B2SLL observables to fit the model parameters.
So basically explain it, basically extract the model parameters, and then get a prediction for B2S nu.
Yes.
Thanks. Are there other questions?
I have one question.
Yes, yeah, please, Otari.
So my question is following. Whenever you, let's say, violate flavor, or let's say you modify Z boson, then there is contribution in standard model raw parameter. So do you estimate how much this will alter this raw parameter?
Yes. We have calculated, and also we have used the invisible Higgs width as well as invisible Z prime width to constant the new parameters.
And since recently there was that this, let's say, these anomalies in W masses are gone.
Yes.
So how much it constrains, let's say, the other sector?
So for W mass anomalies, we need the Z prime mass to be of the order of MeV, but here this Z prime mass is around GeV, 1 to 6 GeV. That will not explain the W mass anomaly.
I see. Thank you.
Other questions?
I have one.
Yes, please, Ray.
I was just wondering about your view on the role of QCD uncertainties in some of these observables.
Yeah, QCD uncertainties are there, so people are working on it, and the uncertainty, I think it will be at best 20%. And once we include the uncertainty, or properly those uncertainties are calculated, after that only we can make some comment about the B2S mu other observables. Because the QCD uncertainties, their impact on RK and RK star is less, but they significantly affect B2S mu transitions like branching fractions and optimized observables. So there should be some around 10 to 20% effect from QCD.
Thanks.
So how about P5 prime there? Because that's also a ratio.
That is also ratio, but still there will be some QCD effect.
Yeah. Thanks. Other questions?
What about this B sub S to mu decay? Because I thought that people also discuss, I don't know, kind of long range versus short range contribution. Because I think you said that it's a clean observable, right?
No, all the observables in B sub S to
mu. That's
yes.
what I mean. Yeah. Isn't there like an ongoing discussion on?
Yeah. So B sub S to mu is now, it is almost consistent with the standard model. So this December 2022, there is only 0.4 sigma discrepancy between standard model and this experimental observable, both CMS and LSCP.
Okay.
I have another question regarding that other model which you presented with the U1 lepton quark.
Yes.
So you looked at neutrino masses
Yes.
there.
Yes.
Did you think there also about UV completions of that model, or is that you
No.
basically just added?
We just added because
Okay.
UV completion will be difficult if with U1 lepton quark.
Yes, yeah. So you have to extend the gauge sector.
Yes. We just consider only U1 lepton quark and there's scalar die quark.
Yeah.
What's the role of this scalar die quark?
Because we need to explain the neutrino mass, and with a vector lepton quark, you cannot generate the neutrino mass. With this scalar die quark, you can generate the neutrino mass at 2 loop level. So basically, we tried to explain the flavour anomalies, neutrino sector, as well as Anita anomaly.
But one more question on that. So with RD and RD star, right?
Yeah.
So the if one looks at the data, so I think it was just slide 27, is that right? Where the latest HLA fits were?
Yes, this is the latest.
Yeah, that's the latest one. I guess, okay, so it's easiest to see if one looks at the numbers, right? So
Yeah.
there is RD star is now quite close.
Yes.
So for that, it's just for RD, I think there's a typo, right? There's a
Yeah.
instead of a 3.
Yes.
There it's further away. So does that mean you always need a scalar operator, or so you can never do it with a vector operator? So you basically, when you showed this, the vector operator contribution was
Vector operator, the
contributes
first
in
one,
the same way.
VL type, yes,
Yes.
standard model type.
Yes.
So I think one can also try with a right-handed current, because for the RD star, it will contribute as 1 minus VR square or 1 minus CPR square, whereas for RD, it will be 1 plus CPL square. Since the deviation in RD star is less, I think it will be like possible to consider also the right-handed current.
So basically a left-handed current plus a right-handed current.
Yes.
So it more or less stays the same for
Yes.
RD star, but you have
Yes.
a large effect. Okay. Now that makes sense. Any other questions? Or from online? Good. I think we exhausted all questions. Yeah, so thank you very much.